All right, so for lesson 5, I wanted to finish up the standard atmosphere discussion. I'm sorry I didn't get around to finishing it. We had a lot to cover today. This is for lesson 5 in Aero 210S. Just a short discussion on standard atmosphere and what it means, what these words mean, and hopefully how to do some of the problems. So you have to know that as we change altitude, as we go up in altitude, the properties in which we discussed, temperature, density, velocity, change, as well as the speed of sound. We have to account for that. So when we're designing aircraft, more importantly, we have to be able to communicate between different entities, say a designer in Europe and a designer in the US. To what standard are we going to build to? And if we agree among each other to use a standard platform, for example, the standard atmosphere, our design should be better aligned. Now, in truth, there is no such thing as a standard atmosphere. The atmosphere is very dynamic and it changes everywhere. But for our purposes, there's a standard atmosphere, and there's a standard atmosphere table in Appendix B in the back of the book. Please turn to that and follow along with me as we discuss the remaining slides here. So, interestingly enough, if you grab data, this is from Denver International Airport, and you compare it against the model, which is the blue dashed line, it follows it pretty darn close. The green line represents actual data from 18 January 2020. What is the atmosphere doing? Well, as you go up in altitude, look at the horizontal axis here on this chart, and you'll see that the temperature is actually, as we go up in altitude, the temperature drops. The temperature is dropping, but then it pauses. This is called the tropopause, essentially where temperature stops and then starts to warm up again. Well, why the heck is all that happening? There's so many effects, from ground warming to ozone to distance from the sun to thickness of the atmosphere, that is actually helping to build this temperature profile. And as we get further and further up, closer to space, it eventually does cool off, it does warm up, as you know, that being an astronaut out in space in front of the sun could be extremely hot. So how do we build our standard atmosphere model and the standard atmosphere table? Well, we're using two equations. We're using the perfect gas law and the hydrostatic equation, but we're also using empirical data from weather balloons, sounding rockets to help build this model. Our equations, the lapse layer, the lapse rate, is what's happening in the changing layers. The isothermal, iso being not changing or staying the same, are these layers here, and there are the associated equations. Now, Chapter 2 does an excellent job at walking you through how to interpret these equations and how to solve for them. There are several excellent examples that I'd like you to practice in understanding how the standard atmosphere is developed. I'm going to show you just a few images of what the standard atmosphere looks like in a model. And on the right side image, there's a change in density, pressure, speed of sound, and temperature as you go up in altitude. Now note that these are in kilometers. So you'll have to make those conversions to miles, so that if you're in the US, you're a little bit more akin to or more familiar with that. And here's some practical examples of what fly or what is up in that particular level of the atmosphere. These are fabulous images to help to really capture what the atmosphere is doing and their temperature and property profile. Here's another one I like to show. Lots of good images. Commercial jets, weather balloons, altitude, again in kilometers and miles here, Mount Everest, weather, right? So there's plenty of atmosphere above even where we fly or where the weather occurs. As I mentioned earlier, there's several ways that this is developed. Weather balloons, sounding rockets being one of them, the ideal gas law and the hydrostatic hydrostatic equation. This is testable material, how the standard atmosphere is developed, so please know those, as well as be familiar with the model equations from chapter 2. Again, it's a lot of background information. We're going to be using this as a tool. I just need you to know how this is built so that you understand that it's not strictly a black box. Okay, and when you go to Appendix B, there's 2 tables, one for each unit. I'm jumping up and down here to foot stomp because one of the things you need to know is that students often confuse the two if they're not careful. I want to just highlight a few things. So I hope you're following with me in the chapter on Appendix B. The header information is very useful. It tells you the symbol, the unit, and its name. So, for example, altitude, pressure, P, pounds per foot squared, speed of sound, A, in feet per second. And you can do trend analysis. The numbers are getting bigger here, which means we're going up in altitude. What is temperature doing? Well, it's also changing and going down. Pressure, also changing. Density, changing. Speed of sound, changing. Without knowing the math or the values, you can simply study this as a trend to see what is happening in the atmosphere. And if you go further down, it'll be very clear that the isothermal layer is making its appearance as temperature becomes constant and then starts to warm up. That tells you you're transitioning between the two, or the layers of the atmosphere, the troposphere, stratosphere, and then the tropopause. So look at the standard atmosphere for English on the left-hand page, and on the right-hand page, look at what temperature is doing. I'll pause here for a second. We will be using the standard atmosphere table a lot starting today. One thing you need to know, in order for you to use the entire table, we have to assume a standard day. You'll hear the word standard day or standard atmosphere. If that is the case, all the elements for a given altitude are viable or allowed for a particular problem. If it's not a standard day, you have to go back to the equations, perfect gas law, manometer, or the model equations to calculate values. I'm going to say that again. If the assumption does not say standard day, you can't use all the elements of the table. If it does say standard day or standard atmosphere, you may use all the elements of the standard atmosphere table. Let's practice a problem. Oh, before we go too far, there's several ways to measure altitude. We can measure altitude on the pressure column, the temperature column, or the density column. Density altitude is of particular interest to aviators because the amount of air mass at a particular altitude will influence the performance of aircraft, right? Particularly lift and engine performance. So density altitude is critical. And if you're an aviator down at the airfield, you'll know that the gliders and some of the aircraft are density altitude limited. The other one you can also measure is geometric altitude. Essentially, the saying goes that if you were to roll a tape measure out of the airplane all the way to the ground, you can measure geometric altitude. Oftentimes, we measure altitude in pressure altitude. That's often what displayed, but it's calibrated or adjusted for the density of the day. So please read through this. Understand that there are 3 altitudes. The one pressure altitude is denoted by H sub P. This is H sub T for temperature, and this is H sub rho for density altitude. Those are the 3 we're going to work on now. So here's an example. If we are at an altitude of 6,000 feet mean sea level, and the temperature is 55 degrees Fahrenheit, the pressure altitude, H sub P, is 7,000. What are the temperature and density altitudes to the nearest 1,000 feet? So we could probably assume this is probably geometric altitude, but now we're going to account for altitudes given the air pressure. And that matters because air influences how the aircraft performs. So we need to know the pressures temperatures and densities at these various altitudes. So the first thing I want to do is make sure I've converted my Fahrenheit, which I do here. And now go to the chart and look up on the standard atmosphere chart, 515 degrees Rankine. 515 degrees Rankine. Now, for a non-standard day, which this is, because it doesn't say standard day, you're going to go to the table and look it up. Unfortunately, as I'm giving this little talk here, I don't have my book handy. I'm not well prepared. Here it is. So if I go to 55 degrees Rankine in my table, and you should be doing the same right now with me, on 515 Rankine is about 1,000 feet in altitude. So what is this value? This is equal to H sub T, or the temperature altitude. All right, how do we solve for the density altitude? Well, what do we need first? We need the perfect gas law. P is equal to rho R and T. Well, we just solved for temperature. The gas constant for air is from the back of the book. Please make sure you use the right one, Aiden. And then let's import our pressure for 6,000 feet, which is 1633. And I'll double check that in my book. You can do the same. Oh, I'm sorry, I'm on the wrong pressure here. 1633 is 7,000 feet, so we're going to use H sub P there. H sub P. H sub P. Okay, and we're looking for H sub rho. So when you do the calculation, you end up with, and you solve for density, we're solving for density here in this equation, you're getting 0.00185 slugs feet cubed. And that, on the table, corresponds to closest value 8,000 feet. So you see, on a non-standard day, given various temperatures and pressures, we are not all aligned at one altitude as we would on a standard day. Let's try another one, this time without the equations in front of us. So we have instruments, we have a temperature conversion ahead of us, and we have a pressure altitude of 7,000 feet. What is the density altitude? So in the interest of time here, I know I'm going to convert this temperature as 82 degrees Fahrenheit to Rankine. Boy, that's really terrible. I'm using the mouse trackpad. And what's the conversion? Well, if I go to page 569, and my conversion tables, I know that the conversion is, I'm doing this in real time, right? What's the conversion in real time? 569 is adding 460, right? On page 569, so I go plus 460 to convert that, and that gives me 542 degrees Rankine, right? And I have a pressure altitude of 7,000 feet. Well, what's the pressure at 7,000 feet? It happens to be, again, going back to my table, 1633 pounds foot squared, and we just solved for that. 1633 pounds foot squared, right? Pounds foot squared. Oh, that's horrible. I'm going to insert this into the perfect gas law. Pressure equals rho R and T. Okay? And I'm going to solve for density. I'm going to solve for density. So the way this works is we're going in at pressure altitude at a particular temperature on the table. The gas constant comes from page 569. And again, I'm solving for density, right? And I'm going to use the table this time to find density, which eventually leads me to tell the density altitude. And I think the next image will show it better. Oh, there's some equations there. Let me erase my work. So there's 1633. the gas constant, and the conversion for temperature. And that's my density. Remember, this is just density. So what's the closest altitude? Well, let's go to the table. Now remember, we entered the table at 7,000 feet pressure altitude from 1633 and found 1633, and then we calculated the density of 1756, which corresponds to a density altitude of 10,000 feet. So I wanted to get through this portion of the lecture because I didn't get a chance to cover it today in class. This is not very straightforward in the material, and that's why I like to do this example. Finally, what is an altimeter? An altimeter is merely a pressure altitude reading that reads in feet, right? It's a pressure meter that reads in feet. Now this little window here is called the Kalsman window, and you type in the barometric pressure of the day. If you're in aviation, you hear the terms, the altimeter setting is 2992 or 3001, whatever it happens to be for the day. So you can practice these examples here. You can finish off the rest of the lesson, and I hope you have a great weekend. Thank you.